The next topic in Statistics 1 is probability, and this video aims to look at some of the basic features of the probability covered in Stats 1 and some of the notation we use for probability. We're going to have a look at things like sample space diagrams, the addition law of probability, where we have things like the probability of event A or event B happening, and to learn how to use some of this notation like this or and the and symbol. In basic terms then, probability addresses how likely things are to happen. It's obviously useful to know this, and there's a number of fields it's useful in, and some quite stringent scientific methods do involve probability theory. An experiment can have a number of different outcomes, and we call the complete set of these outcomes, of the possible outcomes, the sample space. For example, if we throw a normal six-sided dice, we can get 1, 2, 3, 4, 5 or 6. So that is the sample space. In a general knowledge quiz with 70 questions, the sample space for the number of questions that can be answered correctly is 0, 1, 2, 3, up to 70. An event is something that happens. It's a collection of outcomes from an experiment. For example, getting an even number on the dice could be considered an event, or scoring more than 40 in the quiz. If we let A be an event arising from a statistical experiment, this is the notation we use for the probability that A occurs. P, and then in brackets you can see A there. We usually use uppercase. The probability of any event is between 0 and 1, where 0 is impossible and 1 is certain, and all the other probabilities fall in between. So the closer to 1, the more likely it is that the event will happen. If it's certain to happen, then the probability of A is equal to 1. If it's impossible, then the probability of A is 0. We denote the probability that A does not occur with this notation here. We put a little dash over the A. This is the probability that A does not occur. And the probability that A does not occur will be 1 minus the probability of A occurring. We'll look at a sample space diagram now. This is a diagram for throwing a dice twice and looking at the possible scores that we can get and how we can get them. So for example, if we throw 1 on our first throw and 2 on our second throw, we would get this 3 here, whereas 2 on the first throw and 1 on the second throw would get the same score but in a different way, with the 2 and the 1 being on different dice. We can see here we have all of the possible outcomes, a total of 36, and they're all equally likely to happen provided the dice are fair. We have 5 outcomes that result in a total of 6, so that tells us that the probability of a total of 6 is 5 over 36. We could apply the same logic for a total of 7, where the probability is 6 over 36, which we would simplify to 1/6. We sometimes use Venn diagrams to represent probabilities. The outcomes that satisfy event A can be represented by a circle, like so, and the outcomes that satisfy event B, another circle. If there's an overlap, if it's possible, that we can have event A and event B both happening, this happens in this overlap area of the circle, where outcomes satisfy both events. We say that two events, A and B, are mutually exclusive if this isn't possible, if they cannot occur at the same time. For example, if a card's picked at random from a standard pack of 52 cards, the event of the card being a club and the card being a diamond are mutually exclusive. It's not possible to pick out a card that is both a club and a diamond. However, the event the card is a club and the event the card is a queen are not mutually exclusive, because we do have the queen of clubs that satisfies both events. When A and B are mutually exclusive, then we say that the probability of A or B occurring equals the probability of A plus the probability of B. And this symbol here represents union. It basically means or. The probability of A or B equals the probability of A plus the probability of B. If we were to represent this by using Venn diagrams, then the circles would not overlap like so, because A and B are mutually exclusive, so there's no overlap. If, however, A and B can overlap, they're not mutually exclusive, then this complicates the addition rule a little bit. The probability of A or B now becomes the probability of A plus the probability of B minus the probability of A and B. We have to subtract this area in the middle where A and B occur. The reason for this is because we've already counted this in the probability of A. We then count it a second time in the probability of B. So if we add them together, we've counted the area in the middle twice. So we need to subtract one of those. Notice we have another symbol now. It's like the union symbol but upside down. And this is the intersect or and symbol. It means the probability of A and B occurring. So when the events are not mutually exclusive, the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. In other words, A circle plus B circle minus the bit in the middle. For example, a card's picked at random from a pack of cards. What's the probability that it is either a club or a queen or both? Well, if we call the event card is a club C and the event card is a queen Q, the probability of a club is 1/4, because there are 4 suits: clubs, diamonds, hearts and spades. They all have an equal number of cards in them. They all have 13 cards in them. So the probability of a club is 1/4. The probability of a queen. Well, there are 4 queens in the pack of 52 cards. There's actually 1 for each suit. So we get 4 over 52, which simplifies to 1 over 13. The probability of a club and a queen is only 1 over 52, because there's only 1 queen of clubs. So to work out the probability of a club or a queen, we simply add PC plus PQ and subtract the probability of C and Q, because remember, the queen of clubs is counted here and the queen of clubs is counted here. So we need to subtract one of those to get the correct answer. And here we have a good bit of practice with adding and subtracting fractions. This is what it looks like on a Venn diagram. Here's our clubs, 13 clubs. We have here the 4 queens and then the queen of clubs in the middle. So 12 clubs that are not queens, 3 queens that are not the queen of clubs, and that's the queen of clubs. Okay, time for you to have a go. See how you get on with this. We've got 2 events, C and D. The probability of C equals double the probability of D, which equals 3 times the probability of C and D. Given that the probability of C or D equals 0.52, find the probability of C and D, and find the probability of C and not D. Pause the video and have a go. Okay, so starting from what we know that the probability of C and D is X. So this is X. 3 times X is equal to twice the probability of D and is equal to the probability of C. So we know straight away that the probability of C is 3x, and that therefore means that the probability of D must be 1.5x, because it's half of that, isn't it? So into here we have 3x plus 1.5x minus x, so we get 0.52 equals 3.5x. So x therefore must be 0.52 divided by 3.5, which is 0.15. For the second part of the question, we're trying to find the probability of C and not D. Well, that's this area here. So it's basically the probability of C minus the probability of C and D. You can see here how the Venn diagram helps. Well, we know that the probability of C is 3 times the probability of C and D. So 3x minus 0.15 that we worked out from the previous part of the question. That gives us 0.45 because that's 3 times x. So subtract the 0.15 and we get 0.3.